Hello students, today we are going to learn about the topic electric field due to a uniformly charged ring on its axis. Let us suppose if you take a charged ring having a charge Q. So our aim is to calculate the electric field with respect to the charged ring along its axis at any point. So let us get into the topic. Electric field. Electric field due to uniformly charged ring. So initially we consider a charged ring here. This is a ring having radius R, and having positive charge on it. The ring having positive charge. So our aim is to calculate the electric field at a point along the axis of the ring. Suppose if we calculate the electric field at this point P with respect to the charged ring, the distance of P from center of the ring O is x. This is the distance which is x. So with respect to the charged ring, we are going to calculate the electric field at point P. Okay. So because this is uniform charge distribution, initially we consider a small part in the ring. With respect to that small part, what is the electric field at point P? We calculate the electric field with respect to the small part of the ring. Later we will integrate to the total radius. So let us consider a small part here. This small part having a charge dq. Suppose the total charge on the ring is q. The small part we choose on the ring having charge dq, and the distance from dq to point P. The distance from dq to point P is root r square plus x square. Because r is the radius of the ring, x is the point, we are going to calculate the electric field. So dq is the charge. With respect to the charge dq, the electric field at point P is directed away. Because this is positive charge, electric field is away from point P, and this electric field is dE. Because small charge dq produce electric field dE at point P, and let us suppose the angle is here theta, so that dE is divided into two components. If suppose the angle taken here is theta, this is also equal to theta. So the dE is divided into two components, dE cos theta and dE sin theta. So the electric field dE is divided into two components. One is dE cos theta, another one is dE sin theta. But due to the symmetry, dE sin theta components are cancelled, because if you take the charged portion here, this is dE sin theta. If you take here, the dE sin theta is in upward direction. So these two components are cancelled. Finally, the resultant electric field DER is equal to dE cos theta. So the resultant electric field is DER is equal to dE cos theta. If you integrate the part DER, then we get the total electric field with respect to the charged ring. So DER is equal to dE cos theta. So here, what is dE? dE is the electric field with respect to the elemental charge. So electric field relation we know, K into dq by distance square. Here already distance is root r square plus x square. If you square it, then it is r square plus x square. This is dE into cos theta. DER is equal to dE is k into dq by r square plus x square into cos theta. Cos theta is equal to x by root r square plus x square. See, in this triangle, cos theta is equal to adjacent side by hypotenuse. So that x by root r square plus x square. So finally, DER is equal to k into dq into x by r square plus x square whole power 3 by 2. This is DER. That means small electric field with respect to the charge dq. And then we integrate to get total electric field. So by integrating on both sides, integral of DER is equal to integral of k into dq into x by r square plus x square whole power 3 by 2. Here the integration limits are 0 to q. We integrate to the total charge 0 to q, because small portion having the small charge, we integrate to the total charge 0 to q. So ER, the remaining kx by r square plus x square whole power 3 by 2 into integral of 0 to q dq. So finally, the integral of dq is nothing but q, so that the resultant electric field is equal to k into x into capital Q by r square plus x square whole power 3 by 2. This is the resultant electric field with respect to the charged ring along its axis at a point, at a distance x from the center of the ring. Okay. Let us suppose if x is equal to 0. Suppose if you calculate electric field at the center of the ring, what does it mean? X is equal to 0 at center of the ring. At center of ring, x is equal to 0. X is equal to 0 means ER is equal to 0. So the electric field at the center of the ring is nothing but 0, because x is equal to 0. So similarly, if x is less than r, that means the point we choose is very close to the center of the ring. So x value, if x is less than r, in this case we neglect the value of x while comparing with r, so that in this case ER is equal to, if you neglect the value of x, r square whole power 3 by 2, that is r cube. So kq by r cube into x. This is the resultant electric field in case of x less than r. So what does it mean? Resultant electric field is directly proportional to x in this case. That is the second case. Suppose if you take x is greater than r. The third case, if x greater than r, that means at very large distance. If you calculate the electric field at a point which is very large distance from the center of the ring, in that case the r will be neglected, so that ER is equal to, if you neglect the r, then what happened? X square whole power 3 by 2 x cube, then that is k cube by x square, because numerator having x, denominator x cube, both are cancelled. Finally ER is equal to k cube by x square. So ER directly proportionality to 1 by x square in this case. So the electric field is proportionality to x when x less than r, and electric field is directly proportionality to 1 by x square in case if x greater than r. Okay students, so how the electric field is varied with respect to the distance and where the electric field will be maximum, because at center the electric field is 0 and somewhere the point electric field is kx into q by r square plus x square whole power 3 by 2. So where the electric field with respect to the charged ring will be maximum, next we are going to discuss about that point. Okay, let us see the variation of electric field due to charged ring. Actually, where the electric field will be maximum, we are going to identify the point where the electric field will be maximum with respect to a charged ring. Already we calculated the resultant electric field is equal to k into q into x by r square plus x square whole power 3 by 2. This is the electric field. So where the electric field will be maximum, if you want to calculate the maximum value, then if you differentiate the factor which is equal to 0. So differentiate the factor dr by dx with respect to x, because we want to find the location. So dr by dx is equal to 0. So d by dx of er is nothing but kqx by r square plus x square whole power 3 by 2. Okay, that is equal to d by dx of kq into x into r square plus x square whole power minus 3 by 2. If you take the numerator r square plus x square whole power 3 by 2, denominator to numerator, then its value will be minus 3 by 2. Then kq into, so if you differentiate the factor, initially differentiate x, then which is equal to r square plus x square whole power minus 3 by 2. Next differentiate the r square plus x square whole power minus 3 by 2 factor. So x into minus 3 by 2 into r square plus x square whole power minus 3 by 2 minus 1 into x square differentiation is 2x. This is d by dx, dr by dx. So which is equal to 0. Take it common, r square plus x square whole power minus 3 by 2. Then 1 plus 1 minus 2 cancelled, 1 minus 3x by r square plus x square. Minus 3 by 2, if you take it common, then inside r square plus x square whole power minus 1, that is, so this is 3x square. So der by dx is equal to kq into r square plus x square whole power minus 3 by 2 into r square plus x square minus 3x square by r square plus x square. That is the factor. So to get maximum value which is equal to 0, take it d by dx is equal to 0. Then all those factors are 0. Finally r square plus x square minus 3x square is equal to 0. Then r square is equal to 2x square. Finally x is equal to plus or minus r by root 2. So this is what we find in this. So we differentiate the electric field factor and finally we calculate x is equal to plus or minus r by root 2. What does it mean? From the distance plus r by root 2, the electric field will be maximum, and at the same time from the distance minus r by root 2 also, the electric field value maximum on the negative side. See, this is the electric field. It is maximum here and here. This is r by root 2 and this is minus r by root 2. The distance is r by root 2, where the r by root 2 on the positive side, that is positive peak, where the r by root 2 minus r by root 2 on the negative side will get the negative peak. So the electric field value finally maximum at r by root 2 in case of a uniformly charged ring. So this is about the electric field with respect to a uniformly charged ring. Okay, so let us discuss about the electric potential. Due to a charged ring. The same uniformly charged ring if you take, then what is the electric potential along its axis at a point x from its center? A charged ring having positive charge, so this is point O. So our aim is to calculate the electric potential at a point P, the electric potential at a point P from O. So that is our aim. So because this is uniform charge distribution, we take a small element on the ring, the elemental part of the ring having charge dq. With respect to the charge dq, the electric potential at a point P, initially we calculate and then we integrate to the total charge. So this is the radius of the ring and this is the distance O to P is, let us suppose the distance is x. So what is the potential at point P with respect to the small elemental charge dq? The potential is dV. dV is equal to k into dq by r square plus x square, the distance. We know the relation for potential k into q by x. So that k into dq by the distance is r square plus x square. This is the potential. So by integrating on both sides, integral of dv is equal to integral of k into dq by root r square plus x square. By integrating on both sides, then v is equal to potential v is equal to k into q by root r square plus x square. This is the final relation we get. So v is equal to k into q by root r square plus x square. This is the potential with respect to the charged ring having charge capital Q. Total charge on the ring is capital Q. The potential at P, which is at a distance from the center of the ring, is x. So if x is equal to 0, if x is equal to 0, what does it mean? At the center of the ring. At the center of the ring, what is the potential? At center of ring, what is the potential? See, v is equal to, if you take in place of x is 0, then v is equal to kq by r. The potential at the center of the ring is kq by r. If you take x is equal to 0, that is the potential at the center of the ring, which is equal to kq by r. If x is equal to infinite, the potential at the infinite distance from the center of the ring. In that case, what happened? If x is infinite, then v is equal to 0. So the potential with respect to the charged ring at infinite distance is equal to 0, because the effect of the charge at infinite distance is nothing, so that potential is equal to 0. Okay, and this is about the topic. Today we learn about the electric field and potential with respect to a charged ring. Okay students, let us meet with another topic in the next class. Thank you for watching.